Good evening. Welcome, everybody. Don't forget to write your name and ID in the chat. Before starting the lecture, I just want to go over the e-learning page of the course and show you a few things I have added. Of course, again, I don't have to repeat every time. The schedule here, I update it every time, after every lecture with the
عامل شير بس انت
مش شايف، مش عامل شير. اوكي. Let me share. شو اللي عملته انا بس؟ اوكي. I started the recording. Where is the share? Okay, share. Okay, now you see my screen, right?
صحيح دكتور.
Okay, so just wanted to remind about this class schedule that I updated after every lecture with what we actually covered. So we're in week 7, right? So last time we started with the embedded systems, embedded software design process. And I linked the slides here and provided the video here. Okay, so and on the main page, I've added some material for those who want to know more. I uploaded the new slides that I used last time. And since nobody wanted me to talk about PID, I uploaded a very famous document that is called PID without a PhD that simplifies what PID and how to simply program in C or some pseudocode, how to program a PID controller. It is a recommend for you guys to read. And a compressed folder here, if you download it, you'll find more than one file, 3 files, I think, for the datasheet, schematics, pinout for the Arduino Uno that I believe I'm going to start using today. And, you know, our project, our design project is 2 parts, right? One part is going to be using the SCS12, and the other part, the SCS12, you're going to program it with C or assembly, with or without an RTOS, a real-time operating system, your choice, but we're going to cover it and we're going to show how to install operating system on that microcontroller and use it. And the Arduino board that we're going to use it to demonstrate embedded software design, model-based embedded software design. And this is the easy part, the fastest part. And I think I can run some demos even today for you guys to start doing at least half of your project. I hope you all, tomorrow is the due date for the lab assignment 1. And what did I do? I did something else. What did I do? Yeah, maybe that article I forgot about. Like, today, we're gonna continue talking about embedded software design. And last time, this is what we did. What? Last time, we started talking about what is software design, requirements, what is requirements engineering, tools, types of requirements. Well, we're here, types of, and we started talking about some methods. So we talked about the process, the importance of requirements engineering, that it solves and avoids problems at an early stage, and some recommendations about how to write good requirements. And we're talking here about functional requirements, not the high-level requirements for the product. That is usually comes from the customer or the decision maker or the owner of the product. Some tools, I mentioned some tools. Then we're here. We were going to start with model-based. I updated the slides. If anybody accessed them before, these are a new version. I added some stuff. So when we talk about types of requirements, we talk about functional requirements, non-functional requirements, and constraints. And I don't know, at my time when I was an undergrad, we used to do a graduation project, and it could be a program you do, a circuit you build, a system you build, a research. It didn't matter. It has to be something big that you can graduate and demonstrate what you learned. And what you learned is not necessarily all around design. Now, our institution, after going with international accreditation and looking what the world, ABET and other accreditation commissions around the world require an engineer to have, one main component is the design, ability to design a system, a component, a product, a process within realistic constraints and requirements. So undergrads and recent undergrads who graduate from such schools, and one of them is ours, they see how much we concentrate, and this is a demand because the industry needs that, how to well-define design requirements and how requirements should be written, measurable, testable, traceable, and within constraints. So when you talk about the requirement, functional requirements, the requirements we're talking about, I want my system to work to be able to control an AC, the temperature in a room by switching on and off an AC, for example, if the temperature goes above a threshold, etc. Okay. There are non-functional requirements that your system has to do something in a certain amount of time, for example, response time. You should respond to a push button within 10 milliseconds, not 1 second. Reliability, your system is not allowed to go down, or fail within a percentage. Energy efficient should be battery powered or whatever, okay? Non-functional. Constraints, limit the design choices. Okay, you have a constraint. When you design this product, you're not allowed to use this chip. When you design this requirement, your budget is limited to this. So you'll go avoid a lot of design choices. And we talked about how you specify design requirements. One of them was the text document. And then there are several ways to represent requirements within a graphical method, like flowcharts, model-based tools, etc. And last time, anyway, the time was almost over when I was here. This is a real industrial, and I took just a small piece of it, software requirements document, just like you see it. The blue color has a meaning. Capital stuff are different than lowercase. Highlighted yellow stuff has a meaning. Okay. In this kind of software requirements, there has to be a software engineer to generate executable code, right? And put the requirements that come from some system feature and another system feature from other teams, put them all together within one executable program that runs on a single hardware, and gives you an executable code that you can test and then go back to improve, if you will. So a text type of requirements, flowcharts type of requirements. The requirements engineer can draw it, the software engineer can turn it into code. And then we came into model-based. We're going to spend some time here, model-based tools like Matlab, Simulink, that actually became an industry standard in some industries like the automotive industry. You design your requirements according to rules within, by dragging and dropping blocks, connecting them together, coloring them, etc. This gives the requirements engineer the ability to test some functionalities, because he's designing functional requirements, by inputting some collected data or whatever, executing it or running it through the algorithm, getting results, autocode generation if you want to run it on hardware, or even at a simulation time, and continuously work on improving the software requirements until you're ready. You give it to the software engineer who really autocode generates. This can give you just C code that the software engineer can put it together with what another guy did or another team did and get the production code. And I was here last time. I just a screenshot of some work. I have videos, but you can, Simulink is one, model-based, first of all, is a very important tool that enables you to reuse models and visualize them easily. Experienced engineers can just look at a model, how it's done, how does it look, the colors, and understand everything, and reuse things over and over again. Then don't worry about the code. The code is auto-generated. Just push this build button, you get the executable, put it on the hardware and run it. And I believe, my goal is to do a demo today. With the tools, the visualization tools, you can build your virtual reality setup, world, devices that you want to control, build it, and monitor any signal you want, and see how well your program is running. Just a screenshot. This is a high-level controller, PID controller for 4 control loops that control a UAV. And I remember in the first class meeting, I gave an idea how a quad rotor works. Double click on this block, you go deeper. And the controller here, this one, the PID controllers, oh, here you are. You got this controller, this controller, this controller. You pass messages, read them somewhere else, get the motor correction, whatever. You just graphically do things. Even more, you can even control the real timeness of things. So here you're telling that this piece, double click on this, you'll find some code. You're gonna find this PID controller by double clicking here. But here on the high level, what's in here has to be executed within 100 hertz frequency, 100 times in a second, right? This one also 100 times every second, 40 times, and every 10 milliseconds, right? 10 hertz every 100 milliseconds. So you control the reliability, the real timeness of how your program flow is going to work, and you make sure things. Well, the underground, after autocode generation, how does the software generate this code? It would use interrupts to make sure that instead of using a loop, and we're gonna concentrate and spend some time designing control or any program loops and interrupts, real-timeness when we talk about real-time operating systems. But just an idea, and this is a piece of code that what you see on the screen that is actually running on UAVs that fly. Some of the blocks even, instead of inside this block, you can have more details, get the, this is a PID, right? You get the feedback from an accelerometer or a gyroscope that measures the roll angle of a UAV, what you want the UAV be at what angle, compute the error, right? Run it through a proportional, multiply it by a gain, discrete, do derivative differentiation with a gain and integrate. And of course, when we're running PID in the digital format on a microcontroller, we're working in the Z domain, okay? In the Z domain, not the S domain. And also, instead of using, sometimes you need some complex logic. And see here, something minus something minus something, all ANDed with something, then this is ANDed with many things. This is true if this is more than something that comes from a truth table, etc. So this could be complex, doing all by blocks, Simulink blocks. So you have a choice to use within Matlab Simulink something called Stateflows. So a state flow, something you draw this square, you say upon entry of this block in any entry, initialize these values at 0, read this data, and while you're here, do this and do this. When this condition is true, go to this state. Then when you enter this state, do this. While you're here, keep doing this forever. And like a loop, right? Don't go out before this condition comes true. You go back here, So this is a very simple thing, 2 states, but the thing can go as complex as this or more. You can do, because these are conventional stuff. I don't want you to read what's in here, but you can get into a state, do some stuff, coding, call functions, whatever. If a condition is true, you go here. Here you can, and you may have a condition here on this node that brings you back or continue. Check a few conditions to continue, or if not true, you can go back, get into this state, keep doing this until something brings you out from here if this condition is true, and so on. And see this whole rectangle, solid line, while these are dotted lines, this has to do, these run concurrently, or after one finishes, the other one works. So a lot of details, very helpful. You draw your program, you autocode generate the thing. Okay, so the block, this block here, double click, is a state flow block instead of a block like the ones we just saw. This will can bring you to something like this you can build. Very handy, that make you think about the functionality, about what to do, rather than thinking about the low-level details of how you're going to code things. Yet you're still developing requirements. These are requirements. I want this to happen when this and this and this are true. These are functional requirements. You didn't write them in pseudocode. You didn't write code. Instead of writing them in flowchart, you write them in a way like this. And even the colors, guys. If this was red, and I want red because I made it all red. If this was red, this means that this is a RAM variable. If it was a green, that is something. If it's a blue, this is a calibratable that has to be stored in the read-only memory, and so on. And I have two papers here published, and I wanted to share with you, just to show you. Can I double click like this? No, I have to go out. Okay, to show you some of the power of these kind of things. Here I'm sharing this paper from a while ago. At that time, we didn't have the toolboxes here. They used to call these Matlab Simulink libraries auto code generation. They used to call it real-time workshop. And this airplane flying at PSUT, the code running on it is the code that I just showed you in the slides. This is the code. This is actual code, okay, that is running. Okay. Another example I liked to show is this work by our undergrads that they worked on last semester. And many people don't appreciate this, but people from industry know what I'm talking about. And I'm talking about a personal experience. Model-based design. Model-based design. These are controllers I just showed you, a PID controller, a digital filter. You know, these are things that I built, but and you can go reuse some existing blocks in Simulink. Okay. And last semester we changed the curriculum of one of our labs. They used to do embedded system design experiments using a PIC microcontroller. And we thought, you know, these guys are doing these kind of projects. They're doing the controller, they're using the controller in the class. Why should they do it again? The class is even more complex. So let's do something more useful. So we introduced this concept. Look what, at the end, our final design project, they're using just like us here, an Arduino and Matlab Simulink. This is an example. This student, the final design project, Muad was the TA, right, Muad? This is one example from last semester. The students were asked to control the RPM of a motor to run us at a certain speed. And this has a feedback loop, right? You don't just send an RPM and the PWM signal and the RPM is set, right? The motor specs can differ. The motor can be get exposed to some resistance or whatever, mechanical. So you need to increase the PWM or reduce the PWM signal to. And if you don't know what PWM is, we're gonna cover it. But if you don't have any idea, just ask me. Stop me. Okay. To get the RPM, a PID controller, and I'm talking about personal experience. Undergrads, engineering undergrads in most of the universities in the States, they don't study control. They do not study control. Our undergrads here, we do 5 years in engineering. They study control, but most of the time is spent on what you know what, right? So no, I challenge that if more than 10% of the people really experience these things in their undergrad, that would be a lot. Anyways, but without even having to learn how to implement a PID controller in C or whatever, or a saturation or a hysteresis, or know what A to D is, you can just grab the blocks, build. This is a screenshot from one of our students' code. Okay, here's his Arduino. Here is his motor. He put IR sensors here to count the number of RPMs, number of rotations of the motor. And there is a video, but this is a screenshot. And this is what he has implemented. See, the signal rise until the set point here. RPM, it's like, I don't know, 180 RPM. And there you go. طبعا في noise, there is noise, discrete. You can filter them out. Here's another example. And he took a picture from his screen. See, an overshoot, then he goes back to settle with different gains. An undergrad who can do this in an uncontrolled course is I believe something valuable. So what I wanted to show case here is that model-based control, model-based design reduces the headache, lifts the design engineer to a higher level above the hardware. You don't need to, this code, the same code I showed you, you can just go run it on another hardware by changing the target by a simple setting in Simulink. You don't need to worry about the hardware. What are the registers underneath? What are, while it is much more complex doing it in C, which is the de facto programming languages for microcontrollers, obviously, this in everywhere. Okay, I'm not going to spend a lot of time here. So speaking about the software design process, we put the requirements, we generated the software. The engineers who define the process, define the requirements, should also produce a document that shows how to test the system afterwards, the software afterwards, to check against the requirements they have put for the design. So here comes the VNV, verification and validation. Verification and validation, I put some references here and what IEEE defines verification and validation. Some ISO definitions are a little different. Software engineering people, there are some differences. But when we talk about IVNV or VNV, come on, buddy. Okay. V, verification and validation. Sometimes they like to call it IVNV, independent, because it should be done by an independent third party, not the one who put I put the requirements, I test them. No, I put the requirements, I put the test procedure, somebody else checks them. Okay, independent. The difference between validation and verification, well, the validation, sometimes they are differentiated. Sometimes the verification and validation, people use them interchangeably. This verification or validation, they mean the same thing, but they're a little different. Validation is to validate the end product, the service, the software, if it needs the stakeholder or the customer needs. You don't look at the very detailed functional details. Did this loop produce this? Did this if condition produce this? You don't test these. The end product, did it meet the customer needs, the stakeholder? This is called validation. Okay. While verification evaluates the product or service if it's compatible or it met the regulations, requirements, specifications, the functional requirements of the engineers. Okay. This was a real quick, it can be something as simple as that, an Excel sheet with everything you want to check, some explanation, how to check it, what is acceptable, what is not acceptable, who's going to do the test, okay, and some sample and whatever, okay, but a test that should be done. Okay, so far so good?
Yes, sure.
طيب. Now we have two options. أنا بدي إياكم to answer, please. Don't let only one person. Don't mislead me. I don't see you guys. I don't see you guys. I don't know what you're feeling, what was going on. Would you like us to go build a model-based program, software, and run it on an embedded Arduino I have here on my desk, and show you how to program it and check some different stuff? Or would you like this to be an individual recording, or you're okay with not going through that? I'm waiting answers.
والله دكتور أنا بفضل نسويه هون.
نسويه هون.
يس.
طيب اوكي، ما بديش اكون مثقل دمي عليكم، اضيع وقتكم. اوكي يس.
First time it's good to go with you, Doctor.
Okay, let's do it. ماشي. So first, you choose, you install Matlab on your computer. I'm gonna run Matlab. As I told you, we have it installed on campus, but off campus as a student using your student ID and email, you can buy a very cheap version online, or ask Muad to help you to get access to it. Okay. طيب. What I'm gonna do right now, I'm gonna go build a project. So I'm gonna do and do it like a class demo. Okay. Let's call it. Let me just. One second, please. Sorry. Let me create a folder for it on my drive so I can build the project. We call it class demo 4 model based. Okay, so to distinguish it from the HCS12 demos. Class demo 4 model based. So I'm gonna store the work here and change the directory here. I'm gonna do my work here. So I just only ran Matlab. When you run Matlab, you'll find a button called Simulink. For those who didn't ever use it, Simulink. Click on it. In Simulink, let's start with a blank document, blank model, create model. So let's plan for our program. What do we want to do? I plan for something because I connected the circuit to make things faster. I connected a circuit I'll share with you now. The Arduino, did anybody not use the Arduino before? Very quick, just to show, do you need to see the Arduino or not? Anyone wants to see Arduino for 2 minutes? Or you know it?
For me, I know it, Doctor.
Anybody doesn't know it? Tell me. Anybody didn't ever use or know Arduino?
Yes, I didn't use it.
You want to have a quick look at it? طيب,
Yes.
a quick look at Arduino. Arduino board. We're going to use Arduino Uno. Okay, they call it Arduino Uno. And it looks like this. This is the board. A very cheap board. And I was told like it's like 5 JDs now in the market. Arduino is not a microcontroller. Arduino is this board, okay? The microcontroller is this chip. You see my mouse, right?
Yes.
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 The Arduino, this is the website for Arduino, okay? It's an open source project by Italian people, but the board can be manufactured by anybody. It's an open source project. That's why it's very famous. People started using it. They built a lot of libraries in C that you can just copy paste code you don't understand. So hobbyists love it. The microcontroller is this chip. It is for the Ono revision 3. It's an Atmeg 32 something called like that. Anyways, it's a microcontroller chip by Microchip. But it used to be by Atmel. Atmel acquired Microchip acquired Atmel in 2015, like 6 years ago, and now this is a production. This is a microcontroller by Microchip, the same manufacturer of the PIC microcontrollers. Okay, the board has interfaces, compatible with Shields, has built-in programmers, oscillator, whatever. Okay, it looks like this. This is the exact same one I have here on my desk. A lot of help here. 3 to 8. The data sheet, links to the data sheet, how many pins it has, what are the PWM pins, what are analog, what are digital, A to D, all the features. Okay, the power that you see current pair IO pin 40 milliamps. Okay, a lot of details and even some tutorials how to there's an Arduino IDE that you can use to program with NC with a very rich library. of doing things without needing to worry about the underneath hardware. I'll come to why we're going to use it with Simulink. Another document here is the schematic of by also Arduino, and I uploaded this compressed folder on the drive. See here it shows the reset button, the USB connector, the power supply, the I don't know what this is, some LEDs, the microcontroller itself, interfaces. These are the digital PWM signals, the ones with the tilde next to them. Some built-in LEDs like this one. This is connected to this one, or I don't know where. We'll look at it right now. Power, ground, analog pins to read analog voltage from analog sensors. Okay. All these things I'm talking about, analog, PWM, digital, we're gonna come to in our coming lectures. So this is the Arduino. Simple, it's a board, open source project that uses a microchip microcontroller. طيب. Now we're not gonna use, why are we using Arduino? Because it's cheap, and now it is so popular that its libraries. We want to learn model base. We don't want to learn, the goal here is not Arduino, the goal is model base, okay? Model base, instead of going buying the libraries for a specific hardware you want to use in your company, well, when you go to a company and they want to use a specific hardware, you buy it, fine. Now here, the library for Arduino for Raspberry Pi are already built in as part of Matlab, Simulink. And if you don't have them, when you install Matlab, you don't get them. You'll need to go to apps. So when you install it, you go to apps here and install a package. Design app, install app. Is it install app? No, it's not app. It's called add a package or a software package. Muad, help me. Where is it?
add-ons.
Add-ons. Yes, where is add-ons? And I'm looking for it.
home يعني على اليمين.
Home. Add-ons. And I did it the other
على
day.
اليمين.
Oh, yes, here. You go to add-ons. Okay, add-ons. Get hardware support packages. See this one? Get hardware support packages. And here you just log in with your free Matlab account. Okay. And what I installed is this package, Simulink support package for Arduino hardware. This is the one I'm going to use, but you have a lot of support packages here for Arduino, for other hardware even. Android devices, see, you can program your Android device with Simulink. Different kind of hardware, FPGAs even, Xilinx, FPGA, ARM Cortex-M, this one, see, a lot of different hardware. You use them, so you install it, it adds the packages here. So I'm gonna close this add-ons. How do I close it? Close it, go back here to Simulink. After you install it, if you go to, this is the untitled, the empty Simulink file. Let me save it. Let me save it in the folder I just created, untitled, fine, ما في مشكلة. It's gonna save it. Creates an untitled.slx. SLX is the extension for the Simulink project, okay, SLX. In the previous version, it was called MDL, model MDL. It's still compatible with the new versions of Simulink. You click on library browser. This is what you get. All these things. Some of them are already built in with in Matlab. When you install the support package for Arduino, this is what you get here. So let me see Simulink support package for Arduino hardware. Here you get a lot of blocks. We're going to use them. If you want to use Raspberry Pi, same thing. Go install the support package for the Raspberry Pi. You get the packages for these things. Now, if you want to build packages for your own microcontroller, there are a lot of tutorials to show you how. Okay, you can. Anyways, so this is the library we added. By add-ons, I added the support package for Arduino hardware. The goal, I said again, is not Arduino. The goal is to use model-based. Okay, my Arduino here on my board. So I'm gonna do it on two, and we have 30 minutes. I'm gonna do 2 steps. ماشي. First, the Arduino board. This is the Arduino Uno. There's an Arduino Mega, you know, the Arduino Uno. This is the smallest, cheapest, simplest. It has a lot of pins. Okay, one of the pins is already connected to an LED, which is pin 13. If you don't know, you can go back to the sheet the resources I just shared with you. Yani here to see where an LED is connected to what pin, and you can check the schematic, but it's even easier here. LED 13, there is a built-in LED connected to digital pin 13. What else? PWM is at pin 3, 5, 6, 9, okay. Serial ports, external interrupts, digital I/O. So if you don't want to look here, it's even it's still easy. You can within Matlab. So we want to put an LED, either the built-in or an external, just like what we did last time in the HCS12, and start blinking it. Blink the LED every 500 milliseconds, مثلا. Okay, let's do this step, first one. Then after we do it, we go further. This is a digital pin, digital I/O. Then we go further, we get a potentiometer مثلا. I also have the hardware, I set it up, I'll show it to you. We get a potentiometer, a variable resistor. Okay, connected to an analog port. Read the voltage here. This is a voltage divider, right? You can, if you move it, it's like a radio. You turn it up to 5, down to low, down to ground, and this you'll have a voltage here between 0 to 5, right? The analog to digital converter will convert it to a number between 0 to 1023. Okay, we'll cover these things, how to convert, what these numbers mean when we cover A to D. But anyways, 1023 is equivalent to 5 volts, 0 is equivalent to 0 volt. ماشي. طيب, what about 2.5 volt? Easy, simple, 512 in the middle. ماشي. We're gonna read this voltage and convert the number from the scale of 0 to 1023 to a new scale of 0 to 255. 255 is 8-bit, right? 2 to the 8 is 256, right? 0 to 255. 1023 is 10-bit. 2 to the 10 is 1024, and 0 to 23. So we're converting a 10-bit number to an 8-bit number. We pass it to a PWM model, okay, that will generate a PWM signal that I'm gonna use to control the speed of a motor. Well, the motor, I cannot connect the motor directly like this because it will consume, it says I just saw it in the datasheet. You cannot consume more than 40 milliamps or draw 40 milliamps from a pin, right? So a motor, a big one like this one I was playing with a little while ago, like this one, it draws more. ماشي. So I need an external battery. So I'll use a 9-volt battery like this one. So in this case, you need a driver. You'll need an interface, a relay. ترى اللي بيعرفش PWM and doesn't ask بتروح عليه. If you don't ask, I'm not gonna speak. طيب. I'm gonna use a gate here, like I'm gonna use an NMOS power transistor that I already have here available. This is a data sheet, a power MOSFET transistor, just like this one. It is actually this one here. Okay, gate, drain, source. I'm going to connect it here to its gate. Here's the gate, drain, source. I'm going to put the motor here, connected to the 9-volt power supply because 5 volts from here and current wouldn't do it. ماشي. And switch 1 0 1 0 1 0 to turn on the motor. When it's 1, motor is on, 0 is off, right? When you increase the amount of time, the pulse width, the more current will flow through the motor, right? And it will move in higher speed. If you connect the PWM signal to an LED, what will happen? It will get brighter, right? You get more current into it, it gets brighter. So we're going to do these experiments real quick. See, yani how much? Imagine when we do these in the SCS12, the conventional way, even Arduino in the conventional way, it's going to take a lot of time. See how fast we're going to do.
دكتور بس
Yes, in model.
هلا البي دبليو ام سيجنال
Yes,
اللي بنحكي عنها انه كانالوج سيجنال او انه فاريبل فولتج سيجنال.
it's a digital signal.
طيب ايش الفرق يعني انه؟
طيب PWM pulse width. I thought nobody will ask. Pulse width modulation, and nothing to be ashamed of. And in my undergrad, I didn't know what PWM is. Okay, pulse width modulation. If you have an LED here, well, let's say if you have a motor just like my motor, the one I showed you here, and you provided the battery, the 9-volt battery, and you connect it, what will happen? The motor will start rotating its full speed, right? If you want to stop it, you can put the switch here, right? You close the switch, you run, you disconnect the switch, you stop. How can I change this speed of the motor? Slow it down.
ممكن اقلل الفولتيه عليها.
قلل الفولتية across it. So how do I do that?
مقاومه.
Put a variable resistor here مثلا.
Yes.
So you can change the voltage across here. So the voltage here will change, right? Because it's a voltage divider now. When the voltage is less, the motor slows down. That's true. That is completely true. However, this will not give you, there is some drawbacks here. First, you're wasting energy here, right? You're wasting power in the resistor. Second, the motor, for example, has to have at least مثلا 8 volts or 7 volts across it to work. Depends on its system. So after a certain point of time, you're going to go below 7 volts, the motor will stop, right? So you will not have the full range of the speed from minimum to maximum, right? From 1 RPM to 1000 RPM. You will have, after 7 volts, it will work, and it will give you some RPM until the maximum, right? Not the whole range. So imagine we have this. Same here. If you replace the LED, an LED replacing the motor, changing this will change the brightness, right? طيب. If I want to control the motor speed, of course I cannot. I can think of another way, and like having a switch here, a switch. A push button. When you push the button here, push button. When you push the button here, the motor will turn on its maximum speed, right? When you disconnect it, so when you push the button, the motor, so here is 0 speed, button not pushed, push button equals 0, push button equals 1, يعني pushed مثلا. And this is speed. 0 is 0 speed, and 1 is full speed. So you're off, you push the button, you go to move to full speed, right? You release your hand, you disconnect you open the circuit, motor will go to 0 speed, right? Until you push it again, goes to full speed. And you push it again, goes to 0 speed, right? This is true actually. If this switching on is switching off in terms of seconds, مثلا. But what if I replace this switch with a digital switch? Yani get a microcontroller here, a microcontroller unit, get a digital switch. Yani like this one, and just like the NMOS transistor I just showed you, right? And connect it to the battery, right? The positive and the ground or negative. And when I write a 1 here, the motor will move on. The current will flow through the gate, right? An N channel will happen. This is an NMOS. The motor will move in its full speed. When I write a 0, the motor will stop. But what if I turn on and off, on, off, on, off the motor in مثلا every 5 milliseconds? This is a mechanical device. It cannot stop. It will have an inertia, right? It cannot stop in 5 milliseconds. It will keep going, right? So here you're allowing current to go through. It will move. Here you're stopping. So you'll have here maximum current, right? So if I have to draw the current, here you'll have maximum current. When you switch off, here 0, any voltage here is 0, the N channel will disappear, the current will go to 0. But in 5 milliseconds here, if this period from here to here is 10 milliseconds, sorry, from here to here is 10 milliseconds, half of the time you're on, half of the time you're off. When you go off, the current, it tries to go down, but it will not. It will not. Then it will rise, right? It will look at like something like this. When you turn on, you'll go to maximum current, but there's a rise time. When you turn off, it's really fast. The current will not go to 0, so the motor will keep going with a less speed. If I play with this pulse width and make the amount of time that the pulse is lower, 10 milliseconds here, I have 50% duty cycle, 50% of the time was on, then we're talking about 50% of the speed. The motor is going to move in half speed. If I do it 2.5 milliseconds on, and then 7.5 milliseconds off, and repeat this again forever, then 25% of the current is going to flow, and the speed is going to move. The motor is going to move in its 25% of its speed. Yet, in all cases, when it's on, it will have its 9 volts. The voltage is not going to drop. So you'll have the full range. So by varying this pulse width from nothing, 0, to all ones, all the time it's on, this is full speed, to 50%, to 25%, whatever, you change the speed of the motor. Replace the motor with an LED, you'll change the amount of current the average amount of current going through an LED that will affect its brightness. Understood? Varying the pulse width here, we call it pulse width modulation. Clear, Mustafa?
تمام دكتور, yes.
Okay. So this is what we're going to do today, and I'm going to show you this pulse width on the scope, and see how it changes and the motor speed changes. Okay, let's go build our program. First, before we build, you need to set up. You go to modeling, model settings. See model settings, this gear here, model settings. You click on it first. This is the very first thing you start doing before your model. This is for simulation purposes. When you want to simulate, we want to run actual hardware. But you know what? If you want, it will stop after 10 samples. You can do it infinity. keep it when we want to simulate. We actually want to simulate and we want to run on the hardware. We're going to do things. The solver selection, it's not our yani, topic, but yani, in embedded systems, that's what we do. Go make it this type solver fixed step. You can keep this one at auto. The solver details, the step size, it's better to be the sampling, the ticks, okay? Something, you know, let's say 0.01. Yani 0.01 yani one sample every 10 milliseconds. Okay. Then, so the solver do these, apply. Then here at hardware implementation under diagnostics, go choose here your device. See how many hardware you have? These are the things that already Matlab can support with built-in packages you can download, but you can buy more. See all these Arduinos, Artex, ROS, Xinex, FPGAs, and get more. You can get much more. For us, we're going to use the Arduino Uno. Okay, Uno. Uno. Where is Uno? Here, Uno. Just pick the Arduino Uno, select it. This will change the vendor. By the way, you can generate code to run on the PC itself. Atmel. See, Atmel now is microchip, but yani Atmel. Anything to do here? Nothing. Here, nothing. Mashi. I think just apply. Okay. Okay. What I'm going to do, guys, is go to the library here. I'm going to drag this here. I want to blink an LED. So we need something to click on high, low, high, low, high, low. So you can go to signal sources here in under common and look for a pulse generator here, this one, pulse generator. Just drag it here. Pulse generator. Double click on it. Amplitude is 1. Period 10 seconds. Make it 1 second. And I want to have it the period. You know the period, right? From rising high to rising high. Let's make it 1 second, the whole period. Then we do 50% of it pulse width, yani 50% high period, percent. 50% of it high, 50% will go low. So yani ايش? يعني كأني I did 500 milliseconds high, 500 milliseconds low. Just the same example we did on the SCS12. Okay. Now we want to drag the LED pin 13. You go down to the Arduino hardware support, Simulink support package for Arduino hardware, common. Look for a digital output, not analog input, not analog output, not CAN, not servo, digital input, digital output. Drag this button here. Drag the button, put it, connect it, but the pin, the default here is 9. We want to connect it to the pin 13 that has the LED. How should I know where it is pin 13? Well, you can either go look into the data sheets I shared with you, or just click this button here. You view pin map. You can see the digital pins here when you click this one. View pin map. It will open the map here and show you what's connected on the board on it. So digital output 0 to 13 we're on here. These are the different 0 to 13. You can use any of them for digital output. PWM, you can use these. What else? I think I saw that here it shows somewhere, not here. The LED doesn't show it. Okay, you can. There's a built-in LED at pin 13. Okay, you can check it in the data sheet or connect your own pin. So I'm gonna change this to 13 because the LED is connected to 13. Okay, our program is ready to run, guys. Do we want to simulate it first and see? Well, let me run it, then I'll show you something else. You can, now it's ready to run. And let me show you my setup. Oops, I'm gonna switch to my phone. and connect audio from my phone so you can hear me. I'm gonna طيب what I'm gonna do عشان تشوفوا الشاشة كاملة. What I'm gonna do is come on, deploy, build and deploy and start. First, I put the board into the USB. Okay, let me do it in front of you. I'm gonna deploy. Okay, well, I'll show it on this camera. طيب, what do you see in this camera? You see me, right? Well, what do you see? I'm gonna click this button. Just remember it because I have to stop sharing so you guys can see this camera. How you see me. Now what do you see? I'm gonna connect audio from here. لا مش dial in. Join audio. Now you hear me from the phone, right?
Yes,
Yes.
Doctor.
You hear me, guys?
Yes, Doctor. سامعينك.
Yes, Doctor.
And I want to pin this this to the screen so you can and you can pin the one I'm showing the camera with. Okay, if لأنه لما حد يحكي بينكم بتروح الصورة, so you can pin it. So this is my Arduino, just like the one I showed you, ماشي. The Arduino here, see يعني here is the LED that is connected to pin 13. I have a setup here for the other experiments, but يعني what I want to do, this is a USB. I just want to connect it to my computer. It takes a COM port. Okay, I'm gonna go build and deploy. I'm gonna go to Matlab. Where is Matlab? شو بصير? Cannot minimize Zoom when you are recording this meeting. Okay, I cannot. ماشي. Go to Matlab. Here's Matlab. Start, build and deploy. Now it is building. See, something is going on here, working. And now, and on the board, it's going to start programming, and I had the program on it. Now you'll see the transmit receive here. You're going to see them start blinking and turning on when it starts programming, because the data is going to be sent serially from my laptop. See, now it's programming right now at this moment. It's done. This is LED. This is LED blinking, half a second on, half a second off. Do you want to make sure you want to check that if it's correct? You can see it on the scope. I have a scope here that I got today, and I want to connect it to pin 13. Okay, انطعج. Is it pin 13? No, fact. It is blinking. Look at my scope. I want to play with this scale. What? No, what am I going to do?
ممكن دكتور لو تعمل اوتو للسكوب.
It's like disconnected. What? Ground disconnected. Is the what is the scale of the voltage? 200 millivolts. Here, 2 volts. It's jumping. Auto. لا. طيب. 2 volts. See it?
See it?
Yes, Doctor.
Yeah, يعني if I'm gonna freeze. How do I freeze here? So look at the time high. My square is 2 volts. The time is 200 milliseconds. Look, it is like 2.5 squares, right? So exactly high, 500 milliseconds high, 500 milliseconds low. تمام? This is the LED working. And here on my screen, let me go back to share screen to do the other part. So I'm going to connect for a second here.
Now, you hear me now back on my laptop?
Yes, Doctor.
طيب.
Yes, Doctor.
And you see me. And okay, and I'm gonna share again my screen. And this is what I got. I got this. You know what? ert.main.c. Open it. This is the auto-generated code by Matlab. See, it wrote the code for us. You can just take this code and run it if you want. It is a machine-generated code. Usually software engineers revise this kind of code, okay? Optimize it sometimes. But anyways, you get an executable and C code. Now, if I don't have a scope, you guys don't have a scope at home, right? And you want to simulate. And by the way, the hardware now, I can disconnect it, connect power, it's standalone running, okay? And the code is there forever. But if you want to monitor it, you can say monitor, connect monitor, طيب, and go grab a scope from the library here, and there are sinks maybe. Okay. Untitled rebuild. Okay, I'm going to rebuild. I know. طيب, under sinks, grab a scope, put it here, connect it, and I'm gonna choose here connect, then build. Okay. Yani connect means go make a piece of software code. When you run your program, send it to the microcontroller, make this piece of code, send me the actual thing running on the hardware. So it's sniffing, it will be sniffing, ماشي? So I selected the connect, then I deploy and build. The same program is gonna go run on the Arduino, yet it's gonna be sending serially through the USB back to Simulink the signal it is generating on pin 13, so I can display it on a scope here, a logical scope. Taking a little time, but okay, done. I'm gonna close this code. And now the code is running on the hardware. I don't have to show it to you, and you believe me, right? And run the monitor and tell it to scale. Taking a little time? No? Something is happening in the background. Yeah. No, the program is not running. No, it's programming now. Now it's going to start. Yes. If you see my phone, this is what you see on the screen. What do you see? Do you see my phone into?
دكتور احنا شايفين اصلا عامل شير انت.
لا, the same signal is on the other scope اللي فرجتكم اياه, the hardware scope. طيب. So this is it. Yani you can monitor real time. The thing is working on the controller, yet the transmit receive buttons are blinking because they're sending back to the laptop this signal. ماشي? Okay, now I'm going to do something else. I'm going to add another component. Stop monitoring. The hardware stops running the software because I'm doing it like a hardware in the loop thing. I'm simulating, but I'm not really simulating. I'm running the program on a real hardware, but it's in a loop within another software that's monitoring stuff. طيب, now I'm gonna do something. Let me show you. Let me go back to my. Let me stop sharing. Show you what I have here. طيب انتوا سامعيني من تليفون right?
صحيح دكتور. Yes.
Okay, this is my Arduino. What I did, guys, here on this breadboard, I have what? Here I have a motor, a DC motor. ماشي? Just a simple DC motor like this one. بس ملزق على راسه لزقة. Some tape so you can see it rotate. This is a potentiometer. I connected it to 5 volts and 0 volts, just like the one we drew. I'm going to go back to our drawing on the screen. A voltage divider, basically. So when I turn, I change the voltage. I connect it to an analog read pin. See these pins, the green and blue. If you see my board, they're connected to 5 volts and ground. Then here A0, the red line, comes from the middle connector of the potentiometer, which is the analog voltage. Okay. Then I take the output of the PWM signal. Here is the PWM. Here are the PWM ports. I'm taking PWM 5, PWM 5 to the gate. Here's the PMOS transistor to the gate of the PMOS. The source and drain are connected to ground, and there should be a common ground here, the ground of the battery, and same as in the to the ground of the microcontroller. You should have a common ground. And the drain, one side to the motor, and the other side to the other side of the battery. So a simple circuit. And so I'm gonna program to read the voltage. So I'm gonna go back to my computer now.
I'm back to my computer. And you see me and my screen, right? Now, guys, time is 6:15. Time is over. I'm not going to cover new material. I'm just going to do this example. Whoever has another class has to leave. He can come back and watch the recording. But I'm going to continue it now. Okay. Now I'm going to read the analog voltage coming. If you remember what we draw, this is what we're going to do. I'm going to get, this is the Arduino, the microcontroller unit, Arduino, on pin analog 0. Analog means you can read any voltage from 0 to 5, not 0 or 1 best digital, analog. The analog is coming, it can come from a digital, from a temperature sensor, it can come from a pressure sensor, it can come from wherever. But what I did is the potentiometer I just showed you, I connected it, one potentiometer, it looks like this, it has 3 pins, right? It's a voltage divider. So you connect this to 5 volt, this to ground, and you take this to analog. This is what I did. This is a resistor, a variable resistor. And oops, and what I'm doing here, come on. This resistor, I'm taking the 3rd pin to the A0. So I'm reading analog voltage. The voltage here will be a number from 1023. We'll see from 0 to 1023. 0 to 1023. The 10-bit A to D. We call it 10-bit A to D. It has a separate chapter that scales the voltage that I'm going to read here from 0 to 5 volt, represented as a number, digital number, analog voltage to digital to a number from 0 to 1023. Then I have my motor here that I'm going to control. I cannot connect it like an LED. LED pin 13 is here, right? Is connected directly, but I cannot replace the LED to a motor because it is going to drain a lot of current. So I need to interface it. I interface it using a relay or a switch. So I'm going to use a power NMOS switch connected with an external voltage source, the 9-volt battery I showed you. And to the gate here, I send the PWM signal. PWM signal, okay? This is actually the circuit I just showed you. So going back to our code, back to Matlab. First, where's Matlab? Here. Going back to Matlab, to Arduino, we need to read an analog input اللي هو potentiometer. Okay, so we drag this analog input here. Pin, I connected it to pin 0, A0. You can double click on it, see the map, and check what are the analog pins. Analog pins, analog input can vary from 0 to 5. Okay, and eventually I just put it at the label 0. So A0, so pin number 0. Okay. Here is my sensor or my potentiometer. Okay, and if you double click again, it explains here what happens. It measures the voltage of an analog input. That gives me 12-bit value range. An output of 0 indicates that the voltage equals 0. An output of 4000, 12-bit. And for all other boards. DU for 12-bit. Ono is 10-bit, so 2 to the 10. So the maximum is 1023. So what we get here is a number between 0 and 1023, and we're going to see it on a scope. طيب, what do we want to do with this? I want to move a motor connected to PWM signal pin 5. So I want a PWM here, pin 5. ماشي. If you double click on PWM pin 5 and see the memory map, of course, you can confirm that PWM is any of these, okay? So 5 is among them. You can keep it, but it says the PWM signal can take any number from 0 to 255, yani 8-bit number. 0 is 0, 255 is full duty cycle. ماشي? So the input that we receive, 1023, we get from here, we cannot directly connect it to here because after 255, this would be saturation. It may send, it's wrong. We need to scale it down. So here to scale it down, we can just simply drag a multiplier, right? You can simply drag, go to common blocks, مثلا, and we need the constant and a product. Here, product. And a constant to multiply with. So the product, I want to multiply this number that I get from here, which is a 0 to 1023, with a number. I want to scale down to 255, so I can multiply by 1000, 255 over 1023, right? Right?
مظبوط دكتور.
Yeah. So the output of this will be a number from 0 to 255. You send it to the PWM signal. We're done. We want a scope to see it. Let's see it. Scope. Where is the scope? Under sinks. Let's get another scope. Actually, let's get 2 scopes. One to monitor the value for, you know what? No, let's update the scope, make it 2 input, and monitor the 2 value, the reading and the scaled one. Tools, inputs, where is the inputs? number of input ports 2. Okay. Here, I want to monitor the value from the potentiometer and the value after scaling it. So here you will see two numbers. One is a 0 to 2 to 123, and another is 0 to 255. Let me build the program and program it. So we turn connect monitoring, then we deploy. It is programming. I did not have my, I'm going to connect my battery now.
دكتور لو سمحت
Ah,
هسه انا لما اجي اسوي رن بيسوي بس البلوكات الجديده ولا بسوي الثنتين البلوكات القديمه والجديدة؟
Tintin. Very smart and important question, Yazid. Now, what's going to run first? This or this? The compiler will generate code, put it in a single loop. What was first is going to be first. يعني زي ما تكتب for loop, one part, then the other part. If you want to give priorities, you want to make something more important, meet some deadlines, we need to do triggers and just like what I showed in the slides. I want this every 1 millisecond, this every 2 milliseconds. This is enabled after this is done, okay? These are control signals that we can do. For now, they're gonna. If you look at, we just got the file with the machine code. It's gonna be in a single for loop. It is programming now. It is programming now. I'm gonna move my oscilloscope to the gate and monitor the gate with you guys, which is the PWM signal when it's done. And meanwhile, خلينا نشوف الشاشة بعدين we move here. Then my circuit is ready, but my battery is disconnected, so the motor doesn't make noise. Okay, it is still programming. The transmit receive are blinking. Still, we're not working. We're not running. It is probably deploying. Is it deploying or what? Start. Okay. Ah, yeah, it's working. I see my scope running here. What's going on? Here, you see the two signals. Ya shabab. I'm gonna start turning my potentiometer. What do you see here? How do I make this fit to screen? Or see, here now I turned it to the most left. You see my screen, right?
Yes.
And the yellow is the signal from the potentiometer. It moves from 0 to 1023, while the blue from 0 to 255. Now I'm gonna start going down, but slowly, so you can see it going down. It's gonna reach 0. I'm gonna go up, then down, so you can see it on a new screen, a new iteration. Okay, now I'm at 0. See, they moved down to 0. This is the scaled one. This is the original one. The PWM signal. Now, please allow me to stop sharing here on this screen, disconnect my audio and connect to. I'm back here at my computer. You see my computer, right?
Yes, doctor.
You see my computer. Now I'm going to connect the battery. The PWM signal here. I'm still okay. Disconnected. The PWM signal is at 0. I'm turning. See, I'm turning this thing to the left. Now, when I turn to the left, see what you see on the scope. If I do auto here and do the scale we know. See, turn more left. The pulse width is increasing. See it? The pulse width is increasing. As it increases, the motor should go faster. Decrease, increase, decrease, increase. Now I'm gonna connect my battery. The circuit is ready, but I'm gonna make it 0 first. يعني عشان يكون طافي.
Now I turn my battery on. The motor, I don't know how I'm gonna do this. طيب. Let's do this. You still see? Shabab, you still see the motor?
Yes.
And the potentiometer, I'm gonna start turning on. More pulse width would cause more feed disconnection here. See? And this is the worst part of the thing I need to show in demos because things are not. See? Do you hear something?
We cannot see the motor now.
لا بديش تشوف الموتور. سامع إشي؟
now راح الصوت.
Okay, في صوت. It's trying to turn, but it cannot. The PWM signal is very weak. Now I'm increasing the pulse width. It started to move. I decrease, moving slower, increase more. See, increase more, increase more. سامعين الموتور بلف أو شايفينه؟
دكتور.
This is the maximum. This is the maximum. I'm going to slow it down. Now it stopped, but trying because there is some amount of pulse width. Now it stopped. I'm going to disconnect, but not to drain my battery. On the screen here, you still see that the signals are transmitted. في noise إذا بتشوف بالvoltage. You can filter these out, but it's not that big deal. Let me go back to my computer real quick.
Okay, you hear me?
Yes, دكتور.
طيب, I hope everything is clear. I showed you everything, the scope on Matlab, the real scope, the actual hardware, and is my screen shared or not?
No.
No, it's not. طيب. So guys, يعني, okay, and I was pointing to something. طيب. This is our software. There is much more to do, يعني, but this was important to show you the importance of. Now, if I want to run this on a different Arduino, not Uno, Arduino Mega, just go to the settings, go to the model settings here, change the hardware. You have to have it installed first, of course. Change the hardware, change it, make it a FPGA, do whatever. Your code is there, okay? Now, if you want to do priorities, if I want this thing to run every 10 milliseconds, then this, yani, to meet hard deadlines, I can just go make this, okay, right? I'm going to try to finish this so we don't come back and forth a lot of any. Select what you want, right click, create subsystem, create subsystem from selection, Control G. Now you have a subsystem for blinking the LED. It's going to keep running, but if you want to control how fast it runs, yani, you can go to ports and subsystems and have an enable here, an enable or a trigger. Enable, that means what's inside here will be working while this is on, or there is a trigger if you want. It doesn't matter how long it stays, but you don't work without a trigger. So go inside here, go here, drag this trigger here, throw it anywhere, go up. Now you have a trigger. Okay, I can get another clock source and make that this thing run only after every, put it in a loop, run it every 10, not 1 second, every مثلا 0.01 يعني every 10 milliseconds, صح؟ 50% well, period, yeah, 10 millisecond, make it 20 millisecond, 20 millisecond. So half of the time on, half of the time off. If you want, this is real time, any RF2, any you want it really fast. If you don't, you can decrease it to any 200 millisecond. Just check it every 0.2, 200 millisecond. Keep it enabled for 100 millisecond, 50% or 100%, whatever. Then off, and this will be, and you can do the same here. And here, what I did, run what's in here every 200 milliseconds. You can make another loop here and create a subsystem for it with a trigger or an enable for any, so you can manage the time how your program will run. If you want this piece to run after this piece, well, you can go modify the generated code, but you also can send an input that comes from here, okay, an output that comes from here that would trigger the input, a trigger for this subsystem to run afterwards, not during or before. I hope this was clear. I'll upload the code we did together, this code. I'm gonna undo this subsystem thing because we did not run it. Okay, just to keep, I'll keep the code we ran. Okay, save it. This is the code we ran. I'll upload it, and if you have any questions, you can stay until I stop recording. I'm stopping in a second. Thank you very much. See you next week.